is not yet started. Let's wait for a minute for the recording to start. Yeah. So we will be discussing about the execution of memory reference instructions today. Thereafter, if time permits, I will talk about the input, output, and interrupt. Okay, and uh, we will complete this topic in the next class then. I also want to reserve some part of today's class for a discussion of the execution of the register reference instructions that we had done last time on the CPUSim. So I want to illustrate, give you a quick recap of what we did on CPUSim that day. Then there was some queries about setting up the halt bit. So I'll take you through that, and I'll also illustrate that on the CPUSim. Okay, but first let us start with the execution of memory reference instructions. Okay, so the first memory reference instruction that you see on your screen is AND. Okay, now what happens internally when AND is to be executed? Up till this point, that means when we are in the execution phase, you already know from our previous classes that we have already fetched the instruction, decoded it, and the opcode implied that it was a memory reference instruction, and it happens to be AND in our case. Okay, so we have gone through all those phases, and if this was a indirect memory reference instruction, then please uh, let me remind you that in that case, we before we reach the execution phase, that is what we are going to discuss today, we have also passed through an indirect phase. So in case this was an indirect memory reference instruction, in the indirect phase, we visited, we accessed the memory again to fetch the effective address in the of the operand with which to perform the memory reference operation, for example in this case AND, into the address register, right? So in the indirect phase, we have transferred the actual effective address of the operand into the address register, and after that the execution phase begins, right? Now today we are going to see this portion of, we are going to blow out this portion of this instruction cycle flowchart, and we will see how actually these different memory reference instructions are executed, right? So I already have the effective address in the address register. Okay, so the MAR, this notation now donates the contents of the memory at this address, that is the operand, right? So all I have to do is, when the opcode is AND, all I have to do is I have to AND this operand with what? I told you accumulator is automatically implied, right? So we get this operand from the memory whose effective address is in the address register, and we AND it with accumulator, and the result is again stored back into the accumulator, and that is all. Is this clear? Any
Yes, ma'am.
problem?
Yes, ma'am.
Right. Now,
Yes.
the next memory reference instruction is add. So the only change that you see is that we have put a plus sign, that is that represents addition instead of and there is something else that you see here then. What is this? When this is an add operation, then as you are aware, we may also get a carry out from the last bit, that is the most significant bit, which is also known as the carry out. So we store that carry out in the whatever is the value of the carry
Extended
out.
bit.
If there is a carry out, it will be 1. If there is no carry out, it will be 0. So whatever is the value of carry out, it is stored in the extended bit. Any problem up till here?
No, ma'am.
Good. Next, let us proceed to load into AC, LDA. Okay. So as the name suggests, load into AC, the operand, this is the operand, right? Operand is simply loaded into accumulator. Any problem?
No, ma'am.
No, ma'am.
Next is STA. So what do we do here? We simply, STA stands for store AC into where? This location. Okay. So now whatever is the value of AC, it is stored at the address pointed to by AR. Is this clear? Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
If you relate this with one of the instructions in C++, it would amount to saying X. Why? This is a actually a memory address, and X is a variable generally that you take, that also represents a memory address in the background, right? So X is equal to a particular value, let's say, right? So something of that sort, right? Now next instruction is a branch instruction. Okay, it is called bun in short, and its full form is branch unconditionally. Okay, what do we mean by this? Have you looked at the go-to statements in C++? Have you done the go-to statement in C++? Okay, so I advise you to look at the go-to statement in any reference book of C++
It's
or
set
ask,
to coordinates on the screen.
sorry?
It's set to coordinates on the screen, on the console screen.
There are
That's
two
go to
types of
XY.
go-to.
No, no, no. That is go to XY.
The go-to X
Yeah.
takes us to a particular statement in the code where we want to jump to. It's a jump statement.
Yeah. And what is the advantage of this statement? Has
Um,
everybody heard who is speaking? May I know your name, beta?
Ma'am Janika.
Chanika. Yeah, thank you, Chanika. Can you please repeat this so that everybody
Ma'am,
becomes aware?
yes, ma'am. Ma'am, go to X statement, it does what that we set a flag called X at a certain point in our code where we want to directly jump to. And when we write go to X, what it does, it skips all the other instructions in between and directly jumps to that line in the code.
Okay, yes, very good. Excellent. So, you already have you studied functions up now? Have you
Yes,
done
ma'am.
functions in C++?
Yes, ma'am.
Right. So you already know that you can jump to a function, right? The first line of a function, and then the last line of the function returns you back to the same position from where you took a jump. Is everybody comfortable with this thought?
Yes, ma'am.
Yes, ma'am.
Right? That is something which we will look in the next instruction, which is called as BSA, branch, that means jump, and save address. Save Which address? Return address. So you jump to a new location, do whatever is to be done there. So like in C++, you jump to a new function, execute the function, and then don't forget, before you take the jump, don't forget to save the return address so that at the end of that segment of instructions that you are executing, you can return back to the same place. Is this okay? Right. So that is something which we will see in BSA. But what is bun? Bun is a simple jump. Okay. Bun is a simple jump where we don't require to come back to the same location. Okay. So we just take a jump and we don't get back to the same location. That is bun, and it is generally implemented in instructions like go to in higher level languages. Okay, now the use of this kind of branching using go tos is not preferred, because uh, even if you yourself write a program and you have placed multiple go tos here and there, the tracing the program flow later to understand the program, to extend it, or to remove a bug from the program, be it any cause, if you want to return back to the program, and understand and modify the code, then it becomes a big problem, because there are a large number of haphazard, jumps from one places to another. Okay, so that is why functions were created, and every function returns you back at the same place, so you know that okay, this function is working well, so I can skip looking at this function. So I go to this function, it does this work, I had checked it last time, this was working fine, so the bug cannot be here, and then I am returning back here, let me look at the rest of the program, things like that. Is this clear? Right. Now, so next we will see how to implement bun. How to implement bun. So to implement bun, all we need to do is, please see, we need to transfer the address where we have to take the branch into the program counter. Any problem in this?
No, ma'am.
Is this clear to everybody?
Yes,
Ma'am,
ma'am.
one little thing can I ask?
Yeah,
This in this bun, we are transferring the address in the address register to PC, right?
right.
So this address register, the address that is stored here, it's the point where we have written, like, if we talk in C++ terms, the go to statement, or where we have written the X flag.
Yes. So what does this address represent? In case the opcode was bun, then the address in the address register represents the address where you want to jump. Okay, we will just see this with the help of an example. Just give me a minute. Okay,
Okay, ma'am.
now after this, let us come to BSA, branch and save return address, or branch and save address. It means return address. Okay, so what do we do here? First of all, before branching, this is how we branch, right? But before branching, I need to store the return address. And what is the return address? Return address is the next instruction I was going to execute after I am done with execution of this instruction. Yes or no?
Yes, ma'am.
Right? What is the return address? Return address is the address of the next instruction to be executed in the normal sequence before I take my jump, right? And where is that stored? That is always stored in
Program counter.
PC. Yes. So we need to store PC somewhere. Now please see, this is just one supposition that this book does in this basic computer that we have, supposed for ourselves in this book, and we are following the configuration of that basic computer to understand all these concepts. So here they have taken this assumption that whenever BSA will be executed, the return address will be stored at the MAR. Okay, so at the address that I have got uh, from the decode phase or the indirect phase, if this was an indirect memory reference instruction, whatever way I have got the address in the address register, at that place I go and I store the PC, that is the return address, and from the very next place of the of this address which was stored in address register, the ISR will be stored. Now what is ISR? The interrupt service routine. That means the program that I had to, for example, if it was your function, then your function would have been stored where? At just the next position. Okay, so we transfer that to PC. Now let me illustrate this to you so that it becomes easier for you to understand. So I'm just going to, let us please see this diagram. So this is the initial state, let us say. Okay, so at this, I'm right now executing this instruction. Okay, this is my current instruction, it which is at location 20. So obviously PC will contain the address 21, right? Now when I start when I decode this instruction, it turns out to be a direct memory reference BSA instruction. Now what happens? So this instruction says direct BSA 135. What it means is jump to 135, and before that save the return address. What is the return address? It is, the return address here is 21. Okay, so what we will do is I have to jump to location 135. Okay, so I go to this location 135, please see, and what I do there is I store my return address, that is PC. So this is done. PC is stored at MAR. Is this clear? Is this much clear
Yes,
to
ma'am.
everybody?
Yes, ma'am.
Any problem? Any problem to anybody?
No, ma'am.
Right. Now, once this is done, then again this is an assumption that the actual subroutine, that means the function that was to be executed, or the IO routine, that means input output, if some input output was being done, then we call that program which does the input output as ISR, that is interrupt service routine. Okay, so whatever it is, whether it is a normal function or a function to do IO called ISR, it starts from the next location, that is 136. So what we do is we need to assign 136 to PC, right? So how do we do that? We simply say AR, that is 135 plus 1, and we give that to PC so that we can start the execution. Is this clear? Is
Yes,
this
ma'am.
much clear, right?
Yes, ma'am.
Now please see how will we have saved the return address up till now, and we have, let's say, executed the function. How will we jump back to the same location? I need to go where? I need to go back to the location 21, that is this location. Yes or no?
Yes, ma'am.
So how will we do that? Please see. An indirect bun instruction is used for jumping back to the original location. Why? What it says is, please see, branch unconditionally means simply jump to this location. Okay, so I will jump to this location. Oh, but wait, please see, it is trying to say something more as well. The mode bit here is not 0. If the mode bit was just 0, we would have simply jumped to location 135 and stopped. Okay? Yes or no?
Yes, ma'am.
But the mode bit is 1, indicating indirect memory access, right? So this is not the effective address where I have to branch, where I have to jump. Where do I have to jump? That address I will get when I go to this location. Yes or no?
Yes, ma'am.
So what this instruction tells me is go to the address 135 and get the address from there. Now this is the location where you need to branch unconditionally to. Okay, so all in all, it tells me to jump to location 21. Okay, so we jump back to location 21. Is this clear to everybody?
Yes, ma'am.
So with this, please see, we have looked at both the instructions, the execution of bun as well as BSA. If there is any problem, please let me know. Is this clear now? How bun works, how BSA works? So when I was saying bun 135, all I had to do was I had to transfer this 135 into PC. As soon as I transfer this 135 to PC, then this instruction becomes my next instruction to be executed. Yes or no?
Yes, ma'am.
Yes,
Right.
ma'am.
And because this is an indirect instruction, so bun actually is not implying 135, it is actually implying 21. So it tells me to branch unconditionally to address 21. Okay. Now, another type of question that is generally asked uh, from you in the exams sometimes is that what is the instruction which should be placed at the end of a subroutine to transfer the control back to the main function or to the uh, last instruction which was to be executed. Okay, so the answer is indirect memory reference bun instruction. Is this clear to everybody?
Yes, ma'am.
Any problem?
No, ma'am.
Right, good. Okay, so I don't think we have too much time to continue with this today, but that's okay. Uh, I want to devote some time on CPU sim. So let me take you back to CPU sim now, okay? Let me know when you can see my screen. Are you able to see the screen?
Yes, ma'am.
Yes, ma'am.
CPU sim?
Yes, ma'am.
Okay. So if you remember, this was the machine that we had created for ourselves, demo 2021, right? So very quickly, I'm going to uh, first of all create a fetch cycle so that you are able to we are able to execute the rest of the instructions, right? So to do that, what I'll do is, so all that I have done so far in this machine is create these registers and then RAM, right? And this is an assignment that I gave you very early on. So let us uh, create the fetch sequence. So please start speaking up the micro operations for the fetch sequence. Let us see if you remember them.
Ma'am, first step is to transfer the data from AR to PC.
Yes. Why? From PC to
From
AR.
no,
From
PC to AR.
so the first phase is the fetch phase. Yes,
Yes, ma'am.
right. And the address of the next instruction is in PC, right? And that
Yes.
has to be transferred to address register, right? So this will be covered in the
Transfer R to R.
transfer
R2R.
R to
So
R.
I'll say new. See, there are two ways of creating these micro instructions, first of all. So I could have directly gone here and, you know, selected from here what kind of micro instruction I wanted and said new here. And then, so, or I could have done it from the previous interface. Okay, so both ways it works. So let us say PC to AR. So the source is PC. I've done all this with you, right? The start bit will be 0. Destination is AR,
Oh,
and
sorry,
the
A.
destination start bit is 0, and the number of bits is how many?
12.
12, right? Let's say okay, right? So now, okay, so in the fetch sequence, how do we create the fetch sequence? Modify, I say fetch sequence, and from here I get this here, right? So the first thing is that we transfer from PC to address from PC to AR, the address of the next instruction. Now, next, what is to be done? Now the actual instruction is to be transferred into instruction register. Is that right?
Yes, ma'am.
Yes, ma'am.
Right. So how do I do that? I create a memory access instruction. I create news. So there was somebody who was asking me, ma'am, I cannot create a memory access instruction. It is not saying new. Please check whether you have created a memory or not. Okay, this memory I'm talking about. Okay, so if you've not created this RAM, then it will not allow you to do. Otherwise, there should be no problem. Okay, so please check that. Okay, so I say new, and what do I want to do? I want to transfer MAR to IR,
IR.
right? What is the direction? We want to read the memory. What is the name of the memory? I've given it the name, main memory. Where do I want to transfer? I want to transfer the contents into instruction register because I understand it will be a instruction. Okay, and which register will contain the address? The address register. Any problem?
No, ma'am.
No, ma'am.
Do this, right? So now let me get this here, right? Please keep on looking at the order. By default, sometimes, it, you know, jeopardizes the order. So please keep on setting. Now, after doing this, what do we want to do? What do we want to do now?
Ma'am,
Is the job
increment.
done? We have fetched. We have fetched, yes or no? We have fetched the instruction and it is now in the instruction register. But along with this, I must increment the value of PC, right? So I go to increment micro instruction and I say increment PC, right? Which register is to be incremented? PC is to be incremented. Which overflow bit? It is halt bit. So I'll tell you how to set halt bit after this. Halt bit, I have created it, so it is showing me. And with how much to increment? By a value 1. So PC is equal to PC plus 1. अगर दो करना होता, अगर if we had to do PC is equal to PC plus 2, then we would have given 2 in delta, right? So I'll say okay here, right? And let us transfer that here, right? And after that, so this is fetch phase is complete, but as I told you, in CPUSim, in the fetch sequence, we also give the decode instruction, right? So here I'll create a new instruction, micro instruction called decode. So all I have to give it a, all I have to do is that I have to give it a name and I have to tell which register contains the instruction and the decoding will be done internally. Okay. So I say okay, and then I transfer this instruction here, right? Okay, and then I say end. Okay. Any problem? Any
No,
problem?
ma'am.
No,
Right?
ma'am.
So this is our fetch sequence. Now, how to set the halt bit? So in modify menu, go to hardware modules, right? And just a sec. In the register, in the modify menu, go to the hardware modules and in the type of modules, select register, right? And in registers, then when you come down, you will see condition bit. So you select a condition bit and then you say new. Okay. So you give the name. I've given it halt bit. And there is a, we first of all, before we create the halt bit, let's go back one step and I'll show you. I have also created a register here called the status register. Okay. So the first step would be to go to modify hardware modules register and then create a register of 3 bits. Okay. Now, what is this register? You will study this later. In this status register, every bit indicates something. Okay. Now, for example, I'm going to reserve the 0th bit of this status register to signify that halt bit is on. What is the meaning of saying that halt bit is on? Whenever halt bit is on, halt bit is basically a called a control flip-flop. Okay, so one bit is a flip-flop, and we know that the registers are made up of flip-flops. So equivalently, I can say that this status register contains 3 flip-flops. So 0th bit, that is the 0th flip-flop, the first flip-flop, I reserve for, that is going to serve as a control flip-flop, which will indicate to the computer when it needs to halt the program. That means stop the program. Okay, so traditionally in your C++, you put a closing bracket, right, to indicate end. In some other languages that we used to program upon, in COBOL, Fortran, etc., uh, there was a special statement such as a stop or a end or something of this sort. Okay, so the names vary, but the function is the same, to indicate to the system that the program has now ended. Okay, so that is the job of halt bit. When the halt bit is set, it indicates to the computer that the program execution should now be stopped. Okay, so the first step is to create this register of 3 bits, and after that, from here only we go to condition bit and we give the name as halt bit, and then from this status register, I say where is this halt bit located? It is located in the 0th bit of the status register. It is located as the 0th bit of the uh, mm, halt bit. Okay, and then please see there is a checkbox here. It is automatically asking you that if this bit is set, then should I halt the computer? Yes, we should halt the computer. Let me set it to 1. Okay, so initially we make it 0, and then in the program we will set this to 1. I'll show you how. Okay, so for that we will make a stop instruction. The only thing that this stop instruction will do is it will change the value of this halt bit to 1. Okay, is this clear to everybody so far?
Yes, ma'am.
So we have created the halt bit, right, and we have made the fetch sequence so far. Okay, now let us try and make the CLA register reference instruction. Okay, so if you remember how to create a new uh, machine instruction, we could have simply said new, and we typed the name CLA here, and this opcode is given in this in your practical list, and I told you how the opcode is E800. I hope you remember that. Okay, or you can watch the recording of that class, right? And then we had specified what all fields are going to be there in my instruction, and in this instruction, for example, all there is going to be is opcode, which is going to be, how many bits are these? These are 16 bits, right? So 16 bits long. Okay, now, so this is, I have created a machine instruction, but it is empty. Its implementation is empty up till now. So what will happen when I write this CLA instruction in my program? Let me show you. Since it has no implementation as of now, now I write, let's say, CLA. Okay, so this is, it is automatically gets recognized as blue. Otherwise, if I write anything, you will see that it doesn't turn it blue. The reason is that it has recognized that this is a valid instruction. Now, since it is empty, however, if I go on to execute it, nothing will happen. Okay, nothing will happen. Okay, so what we need to do is we need to, before I can execute this, I need to put in the micro instructions that will be executed when this machine instruction is executed. So for that, what do I need to do? We need to set AC to 0. So this is an instruction that we had made last time. If you don't remember, I'll revise it with you. So we come here, we say new, and then we give a name, and then we select which register is to be set. I select AC here. Start bit 0, and how many bits are to be set? All 16 to the value 0. Okay, so I do this, and then let us, okay, so CLA, and now, okay, and then let us put a end here. So again, end is a micro instruction that is already provided in CPUSim. We insert it at the end of implementation of each machine instruction to indicate that there are no more micro instructions which are required to be executed to complete this machine instruction, right? So now this is one uh, machine instruction that I have created. Another machine instruction that I need to create is, please see, stop. Okay, so all I've done is I've said new, and I've given it a name, and I've given it the format as opcode. And here, since your practical guidelines don't give any opcode for stop, I have just, given it C. You can give it anything, right? So for the timing, I have given it C. Now, how to implement stop? So now we will set the alt bit to 1. Okay. And for that, I will either e- either from here you can choose, or you can go directly. See, these are the names you need to see, and you have to understand what do you want to do. So which micro you want to use. So uh, I was searching in set. So there is a special micro instruction, however, to search to set the condition bits. Okay, so this is already made here, but I will show you. There's nothing much to be done here. So we just give the name whatever we want, and then select the bit that we want to set. Abhi tak we have only made one condition bit, right? So it is showing me only that bit, that is the halt bit. And to what value it is to be set? It is to be set to 1. Okay, so I say okay, and then let's transfer this to the implementation window, and then the end. Okay, so this is stop. So I have made two machine instructions for you, CLA and stop, and I'll say okay. Okay, so now in my program, let me just say CLA and stop. Okay, is this clear up till now? Any problem?
No, ma'am.
Ma'am, why are we setting halt bit 1?
Beta, I told you, otherwise there will be no how to uh, tell CPUSim that this program has ended. The last instruction in this program that I am writing, now in this program I have just written one instruction, by the way. Okay, but there could have been many more, right? Is that
Okay,
right?
ma'am. Yes, ma'am.
So the last instruction to indicate the end of the program is always stop. What how the now what this stop instruction does is it should terminate the program, that means stop the program. Okay, how to do that? To do that, we use a special control flip-flop. We we call it halt bit, since its job is to halt the execution of the program. Any problem up till here?
No,
Any
ma'am.
problem up till here?
No,
Please
ma'am.
respond back, beta.
No, ma'am.
So when I how does a control flip-flop work? When the halt bit is 1, then the program will stop. Initial value, if you remember, when we have created the halt bit, we had set it to 0. Now in this stop machine instruction, I have set its value to 1. So that as soon as its value is set to 1, automatically the program will be halted. Why? Because please see from here, where we have told the CPUSim that whenever this bit is set to 1, then you halt the computer. Okay, then you halt the computer. Is this clear? Now,
Yes, ma'am.
whenever you are working, if you have some doubt, you can either refer to my recording, and still if you don't understand something, on any dialog box you can press help. Okay, so as soon as you press help, a graphical help is displayed which explains to you all the parts of that window. Okay, I don't know what happened. Yeah, okay, so you can see here. So it is explaining everything to you. What is a condition bit? How do you create a condition bit? You know, okay, and what is the meaning of halt? Okay, so you can see this halt it is telling you. So it is telling you all the parameters, which register, okay, okay, then which bit of that register, right, and then the meaning of halt bit. So everything is here. Halt is a boolean value. If this value is true, then the machine will halt and display a message. So when I execute this program, you will see that a message halt bit is set will be displayed. Okay, after the execution of any micro instruction that causes the bits value to be set to 1. Is this clear? So this all these detailed information uh, you can also get from the help button. Okay, now let us see how to run it. Quickly, I'm going to do this. So now I want you to focus for a minute. Please see first of all what I'm going to do. I'm just going to this I told you we can change the basis from here. So I'm going to just change the value of AC to, let's say, 1101, okay, before execution of my program, so that I can see whether CLA is actually working. CLA means it should set AC to 0, right? So I have done this, and now I'm going to go to the execute menu and I'll say assemble and load. Okay, now as soon as I say assemble and load, what it does is it will do two things. First of all, it will see whether it will do assembly. Assembly means it will translate this program into machine language, that is binary zeros and ones. That means the opcode of this will be taken and opcode of this will be taken in binary. They will be converted to binary, and then it will load this program, the binary program, where in the memory. Okay, now before I do that, before it does that, however, it is asking me something. Please see, since I have not saved the program, please see, I have not saved this program. So what it is asking me is, do you want to save this? Yes, I want to save this. And what name do I want to give? Let's say I want to give it the name demo underscore CLA. Okay, and dot E. So yes, so this is it. Now can you see what do you see here? Do you see in the main memory in RAM the program has loaded? At address 0, we have the instruction CLA. Yes or no? Can you
Yes,
see
ma'am.
this? Right? And what was the opcode of CLA? E800?
Yes, ma'am.
Yes, please, you can look at CLA E800. And stop was C, right? So effectively 000C. Yes or no? Right?
Yes, ma'am.
Effectively it is 000C. So you can see your program loaded into the main memory. So please see, this is a view that you don't get in any programming, high level programming language. You are executing the programs, but you have possibly never seen this happening. Yes or no?
Yes, ma'am.
So the first step is that your program is taken into RAM, right, for execution. And now let us say run. Okay, let me say run. Okay, now there are two things that have happened. Please see. First, can you see what is the value of AC now?
Zero.
Yes, ma'am.
The value of AC is
Zero.
0, 0, 0, 0. And so the first instruction has worked well, yes or no?
Yes, ma'am.
And then it says execution halted. That means the program is now stopped. And the following halt condition bits are set. क्यों हुई है एग्जीक्यूशन हॉल्ट? क्योंकि हॉल्ट बिट सेट हो गई है. ये काम किसने किया है?
Stop.
स्टॉप ने. ठीक है, तो हमारे दोनों ही काम हो गए हैं सक्सेसफुली. We have done both our jobs successfully. Yes or no?
Yes, ma'am.
Yes, ma'am.
Right? Okay.
Okay, ma'am.
So in the same way, I want you to make machine instructions. I'll just show you. Let me show you the implementation of one more instruction. Let's say CMA. ठीक है, complement AC. So how to do that? So we need a instruction to complement. What kind of instruction will it be? It will be a logical instruction, yes or no? And or not. Not. How will we complement AC? By simply applying not to it, right?
Yes, ma'am.
Yes, ma'am.
So I have named this instruction as logical instruction as complement AC. What is the type of logical operation that I want to do? To find the complement, I want to take
Not.
not. Of which register? Obviously, since I
Accumulator.
want to complement AC, I want to find out the complement of AC. So I want to take the not of AC. Yes or no?
Yes, ma'am.
Now AC, please see, not is a single input gate, but all other logical operations are two input, right? So they have given us a facility of giving two inputs. Now in this case, the second input is ignored. I'm just setting it to AC, but it will be ignored. Okay. In if the logical operation is not, then this is ignored. Clear? Right? And then it is asking me what should be the destination. Matlab, the result after this should be stored in which register? It should again be stored in AC.
AC.
Right? So I say AC and I say OK. Right? And then we put in end. Right? Let's say OK. And now let me just change this to CMA. Okay. And now please, now this is a very important thing that I'm going to say. So after doing this, let us first of all, we need to save this. So let's just save text. Okay, save text. And then before I execute, first of all, I should always do reset everything. Why is this? Because please see the value of PC, IR, DR, every register has some value here, right? Which is the remnant of the previous program. So this is not what you have to do in C++, but here you are doing everything manually and yourself. So you first need to reset everything. Now everything is clear. The memory is also now clear, right? So again, you can say execute, assemble and load. Now please see the opcode has changed. Yes or no?
Yes,
Yes
ma'am.
or no? So actually this is the memory. This is what is there in the memory. This is just to tell you. Okay, this is just to tell you. The comments are just to tell you. These are the actual contents. So it is generally in this form. Okay, but it is easier to recognize, so I am just showing you in hex, right? So now the new program is loaded, and let me just vary the value of AC. So I'm making it 1010. Okay, now let us see uh, whether my program works, right? So we have assembled and loaded, and let us now run it. This is what it is giving me, that the following halt bits are set. This is the value of AC, new value of AC, and this is. So let us see whether this complement that it has done is right or not. So what was my initial value? What was my initial value in AC that I had put? It was 1010 in hex. So it means 0001. आई थिंक इसने वापस उसको 0000 कर लिया एग्जीक्यूशन से पहले. दोबारा करते हैं. लेट मी जस्ट do it again. Okay, let the value be 0000. Okay, and I'm going to reset everything, then assemble and load. Yes, and then let's say run. So please see the value in AC was what? The value in AC was initially all zeros. So now you see all ones. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Right? So in hex it is displaying it to be FFFF. Okay, is this clear? Now there is also, I'll just take 2 minutes more. I know we are way beyond the time today, but just give me a minute since it is in flow. So we can also, you can also use debug mode here. Please see. Let me just reset everything and then show how this debug mode works. So in the debug mode, please see, you can actually see what all micro instructions are being executed. Okay, so first of all, please see, as soon as I've said step by debug mode, and I say step by micro, you see the first thing that is happening is this instruction will be fetched, right? So here it is showing you the instructions or the machine or the micro instruction that is going to be executed. So the first thing that will be executed will be the fetch sequence, right? So we say step by micro. Okay, so I'll say step by micro. So the first thing what it will do is transfer the value of PC to R. Now what is the value of PC? Please see. Initially, oh, I am sorry. Let me just, yeah. Now please see. So my initial instruction which is to be executed is loaded at which address? It is loaded at address 0, right? So the PC has value 0, right? So the first micro instruction should transfer PC to AR, right? So I'll step by micro and let us see the value of AR now. AR's value is the same as the PC. Yes.
Yes, ma'am.
Next is step by micro. Now MAR should have been transferred into the instruction register. That means the instruction, that is E200, should have been transferred into IR. Can you see that happening?
Yes,
Yes, ma'am.
ma'am.
Next, decode IR. So now it is in sorry, and the next was increment PC. Has the PC been incremented?
Yes, ma'am.
Right? And then decode IR. Right? So decode IR. As soon as it has decoded, it has it gone to the implementation of CMA?
Yes, ma'am.
Right? So now complement AC. So please see, AC is complemented. Right? And then end. And now this stop instruction will be fetched and then decoded and then executed. So please see, now up till now the value of AR is 0 and PC is 1. Now PC to AR. So you see that PC has been transferred into AR. Yes.
Yes, ma'am.
Then now the instruction will be fetched into instruction register. What is the code of the new instruction? It is 000C. So 000C has come in instruction register, right? Then increment PC, PC becomes 2, and then set halt bit. This is after that decode. So decode now, implementation of stop accordingly has been loaded here. Yes or no? You can see this instruction stop. It has recognized that this 000C is stop after decoding, right? So it has come. Now it will set the halt bit. Okay. So it will set the halt bit. And as soon as it has set halt bit, it has displayed this message to you. Okay.
Yes, ma'am.
Yes,
And
ma'am.
let me say, okay. Now to turn off this debug mode, you go back and you click on that again. Is this clear? Now, what is your assignment? So on Thursday, what you are required to do, I'll just show you. Can you see my screen? Can you see my screen?
Not yet, ma'am.
Okay.
No, ma'am.
Yeah. So we have already done this. So question number 1 was to create the register set and the memory. You have done that. And then question number 2 is to create the fetch routine of the instruction cycle. You have done this. Question number 3, 4, we will do later, okay, of your practical list. Then question number 5 again. Tomorrow I will be doing machine instructions with you. We have done this today, Hannah. I have done the machine instructions with you. So you can also do this, right? So question number 5, in the similar fashion that I've told you, okay? Question number 7, and question number 8 you have to do. Okay, and question number 9, question number 10. So now you are in a position to do all these. So same way, first of all, uh, for example, I did this instruction with you. CLA I have done with you. CMA I have done with you. So you simply do this. Halt is for stop. Okay, so halt is the, I've taken the name, I've given the name stop, they have given the name halt. So these three instructions I've already done with you. CME is also nothing, you just make a 1-bit register, uh, call call it E, and then you do the same thing that I did for CMA. So similarly you have to do all these other questions. Okay, so now in this week, I want you to complete all these questions. Okay, so now and then your next practical, whenever it is. So both the practicals you use, and so Saturday and Thursday, 2 days you have all batches. You can devote these days to do all these questions. Have I posted this practical list on the group? Have I posted this on the group, students?
No, ma'am.
Okay, I think I did, but it's okay. I will post it again. Okay, and I will also write the question numbers which you require, which are required to be done. Okay, right?
Okay, ma'am.
Okay, ma'am.
Okay. So I'll take your leave now. I hope all of you have marked your attendance.